And if I go over to the right side here, you will see that there is a discussions board. Actually, the exam will be posted here. You can't see it yet. Once this is completed, you'll be able to, once I make it available, you'll be able to see it, hopefully. Okay, right, you can't see it yet. Okay, and, but we have the discussions board. And in the discussions board, there is already set up online help sessions, review sessions, postings for where you can put a question or something like that. There's one question in general, Q&A that just came up. I checked it earlier this morning, so someone must have just posted something. But I will make sure that there is, just like here, exam one, questions and clarifications. There'll be a version of that that I'll put up after we're done here today for exam two, questions and clarifications. And any issues that you have while you're taking the exam, while you are preparing for the exam, you can post them into that link for exam two. I will also, if there's any clarifications, for instance, when we're taking a test in person, there's always a question, maybe the phrasing's a little funny on this question, and somebody will raise their hand and ask for a clarification on it, and they will get some kind of help on interpreting it, presumably. And very frequently we'll write on the front board that, oh, question three, this sentence is a little bit clearer if we phrase it this way or something like that. Or there's a typo and this is what was supposed to be there. Okay, unfortunately, there's no front board when we're taking this online over at each one of us taking it at different times. So I will be posting any updates, any corrections, any typos into the exam two forum that I will create so that you can go there to see, okay, let me go, if there's something that confuses you about question three, you can go there to see if there's already clarification on question three, or if you want to ask for clarification on example three. That way I can give that clarification or respond to that question in a format on the forum where everybody that's taking the exam can see the answer to that and everybody can benefit from it equally. Okay, so please do use the forums because it's the only way for me to communicate with you guys in an online course in a meaningful way so that everybody in the group sees what's going on. So I really appreciate it if you would really kind of go out of your way to use those online forums. And believe me, at the end of the semester, I go back and I look to see who is active in the online forums, who asked questions, who helped, assisted, and answered questions. And I consider that in the grading for the participation and so on, as you can imagine. So let me get into what we're going to cover in this exam. Okay, and this exam is non-cumulative. It's not going to cover the material we covered up to exam one, but it will cover everything from exam one. I forget. I just I'm in the process of updating the syllabus. I may have done it already. I'm not sure in the version that's there right now, but it's covering everything from the session after the exam up to what we've covered now. It's not going to cover analysis of variance. We just took that up this week. I don't want to burden you with that yet. So we'll be discussing that a little bit more after the exam. But it'll cover confidence intervals of means, confidence intervals for proportions. It'll cover the hypothesis testing, which includes the p-test, single sample p-test, independent samples, paired sample p-test. It'll cover proportions. Okay. Now I'm gonna be it's going to be lightweight on proportions because it's a little hard to use SPSS directly for comparing two different proportions, like the percentage of people that are diabetic or prevalence diabetic in one population versus another population from a sample. And but we have something better than that. We have a chi-square test, which we're going to be covering today, which in a sense is kind of like comparing proportions anyway. Okay, I'll discuss that when we get to it. And then I'm also going to cover chi-square relative risk and odds ratio, and we'll talk about that today. Can I go over an example for a single sample? Oh yeah, okay, no problem. We're going to get to that tonight for sure. I'm not sure we'll get to all of this tonight for sure, but we have a few days before I'll be posting the test on Wednesday. And in that period of time, I may be able, if we don't get through a lot today, I'll arrange for kind of another session also. So keep in mind, post in that part that said questions on review sessions. If we don't get to something tonight, remind me to cover it in the next session like this that I do before the exam. In addition to that, remember, it's not like you guys are in a different situation. You're going to be having 2 shots at taking this test. You'll have, as in exam 1, you'll have be able to, you'll get a limited amount of time. You start the test, it's on a timer, you have a limited amount of time to do the exam just as you would in a classroom session. But then you will be able to save your answers. You'll be able to at least get a look at what you got wrong. It won't give you the answers, but we'll give you a look at what you got wrong. Then you get an opportunity to try the test again. Okay, so in the interim, you can always update me, ask me for clarification and questions and so on and so forth. And maybe I can point you in the direction of some videos that we have on Blackboard where we might have covered that, or as well. So you have a little bit of flexibility there. I really encourage you to do the first version relatively early, not before you're comfortable, but relatively early, so that you have a chance to kind of see where you are, and then have time to like really prepare to take it a second time. I had some people that literally didn't do their first session until a few hours before the end of the period, the end of the time for the exam. So they really never, they might have left themselves enough time to do it twice, but not enough time to like really figure out where they might have gone wrong in between the two. So I am going to give you the average of your scores in the 2 exams. So if you get 80 and first time you take it, you get 95 and 96 second time you take it, it'll be the average of the 2. However, I will weight the second exam heavier, the second version heavier than the other, so that you get a little bit better. You're doing well on the second one. Doing not well on the first one will not hamstring you as much as just a plain ordinary happens. So I will weight the second one a bit more than the first one. Okay, so let's move on to what we're going to do, and I'll make sure that we get to that single sample tonight. Okay, so let's talk about confidence intervals. Okay, that's really kind of where we kind of started out this whole set of materials after we got through the first exam. And that'll tie very nicely into talking about the, we don't need to worry about that. I'll fuck it anyway. Okay, so let's talk about confidence intervals for starters. And that'll lead in very nicely into single sample t-tests. Okay, so for instance, let's say that we have a situation where we have a sample. Whoops. Okay, we have a sample. Put it back anyway, didn't we? We have a sample. We take a sample from a population. The size of the sample is, say, 36. Okay, and in some cases, well, let me move on first. Let's say that the mean for this sample, numerical variable that we're looking at, could be, let's say, a sugar level, blood sugar level, or something like that. Let's say that the mean blood sugar level, the average that we found in this sample of 36 people from a population, turned out to be 70. Right now, there's 2 forks that we can take. There's a fork we can take here. One is situation where we know where the standard deviation is, and the other is where we don't know what the standard deviation is. Oops. We don't know what the standard deviation is, and we need to rely on the standard deviation from the sample in order to estimate what the population standard deviation is. Right? So how are we going to do that? So let's say that we calculate our standard deviation from a sample of 36 people, and it turns out to be 12. Okay, so now, in order to find the confidence interval, what was our formula for confidence interval for numerical variable? It's x bar plus or minus. Well, now, we already ran into a problem here, so we got to put in there times our standard error. Now, our standard error is the variability in the samples that we would get from a population if we took the same size sample over and over again. In other words, if we took this sample again from our population, size 36, If another 36 people randomly select from a population, you probably wouldn't get exactly 70 again. You might get 71, you might get 75, and so on and so forth. That's got a lot to do with the variability of the values for the individual people in there. In fact, it's related to the variability, so standard error is equal to the variability of the population over the square root of the sample size. Again, since we don't know what sigma is, we have to rely on the standard deviation that we get from the sample for that over the square root of the sample size. In this case, again, it's going to be n. So in this case, our standard error is going to be equal to 12 over the square root of 36, which is 6 divided into 12 is equal to 2. Okay, so our standard error is equal to 2. Okay, so now we have to decide. We have x bar. We know what x bar is. X bar is in this case 70 plus or minus something times our standard error. Well, standard error really represents the number of standard deviations that we can have between two samples, for instance, between in which we would find 95% of the possible outcomes for the likely mean, true mean of this mu of this population. It represents standard deviations, a number of standard deviations above and below. So we want to find the range which represents two standard errors, two standard deviations below the mean that we're predicting and above the mean that we're predicting. If we know this true standard deviation of the population, sigma, if we know that, we would use 1.96. And why would we use that? Because we know in the standard normal distribution, 95% of the outcomes are between 1.96 standard deviations below the true mean, mu, and 1.9 standard deviations above the true mean. So minus 1.96 to plus 1.96. Well, in this case, we don't know what sigma is, right? We have to use our sample to find out what sigma is. So we can't use 1.96 here. So instead of using 1.96, we use the value. We use the value for the t-score. Okay, so let's see if I can't find that here in one of these values. Use the value for t for that sample size. Okay, so we need our t-table. So I think I have it here. Let's see. Here we go. Okay, Rusty. I think that one's going to be it. Let me spread this out so I can see a little bit better. Yeah, there we go. Okay, so for a sample size of 36, which would represent 35 degrees of freedom, right? In other words, n minus 1 degrees of freedom. So 35 degrees of freedom, we would be using a t-value, a number of standard errors for our calculation confidence interval of 2.06. So I'm going to go back here, and I'm going to put 2.06 in here. So in a sense, why are we using 2.06? We're using 2.06 because since we don't know the true population standard deviation, we're less certain of the spread of our possible samples based on the sample standard deviation than if we had known the true population standard deviation, right? So this introduces a level of uncertainty. We make up for that level of uncertainty by using a bigger value than 1.96. How does a bigger value affect us? Well, if 2.06 is bigger than 1.96, so when we multiply standard error and add and subtract it from 70, we're going to get a wider range. So our wider range is going to give us a little bit more confidence that we captured the true population mean within these two numbers that we're going to call our upper and lower limit for our confidence interval. So this helps us to really be 95% certain for our confidence interval. To be 95% certain for our confidence interval. It helps us to really be 95% certain rather than using 1.96 in this situation, which based on the since we're only basing it on the sample mean, might not be really accurate. Okay, so let's see what that's going to be equal to 70 plus 2.06 Let me find my calculator. 2.06 times my standard error of 2 is equal to 4.12. Let me put that into memory. And I'm going to take 70, subtract my 2.06 times my standard error, which turned out to be 4.12. We have another name for that, right? The name for that is going to be for the name for excuse me, name for that's going to be margin of error. I got distracted. I noticed some questions came up there. I'll be right back on those questions. Okay, that's going to be equal to 65.88. Okay, let's see if I can do that without using everything. 65.88, and this was 4. What was it again? 4.12, did I say? I think it was 4.12. Let me get my calculator back. Okay, and I'm going to clear that. I'm going to put 70 in there, and I'm going to add my margin of error, as we called it. Yep. And it's going to be equal to 74.12. Okay, so we're 95% confident that the true mean for the population that this sample is drawn from is between these two numbers, between 65.88 and 75.12. Well, you know, if I go back, before I answer those questions, if I go back to my t-table, if I happen to still have it here, you may have noticed on my t-table, let's see if I can get a little bit bigger here. You may have noticed on my t-table that as the sample size gets bigger, that value that I use for t, I get more and more certain that it's going to be close to the true population standard deviation sigma. So I can be more and more certain that I can be more and more certain that I can stay within the range for my confidence interval while I'm using a smaller number for my calculation of the confidence interval times where I'm multiplying standard errors. Okay, so as a matter of fact, if you look at this, when I have a small sample, it's 2.28. Use a larger, which causes a larger range. When I use a bigger sample, like 50, goes down to almost 2.01, a little bit less than 2.01. When I get to 100, it's already down to 1.98. So 100 or over, I'm really close to 1.96. So close that when I have a sample size of 100, right? If I had a sample size of 100, or if I know sigma very frequently, instead of using 2.96, I will go ahead and just use 1 point. I'm sorry, instead of using the t-score, whatever it happens to be, in this case 2.06, I'll use 1.96 and instead. So for a very large sample size, say 100 or greater, right? Or when you know sigma, you can use 1.96 here instead. Okay, the last test used 1.96. You know, that was the question, was whether I should use 1.96 or the t-test. It's not really the Gresti number. Gresti is the name of the textbook that I stole that chart from. Okay, but it is the t value or t-score for that sample size. Right, degrees of freedom is 35. Okay, so good. Any questions on that so far? Are we all comfortable with that? Because I'm going to move over now. I'm going to do that for a proportion. Okay, so I'm going to go over here and let's try this again. Let me open up this one so at least it's got the right picture in it. Okay, so now let's see. Let's get another situation. This situation, we are surveying a population, and we're interested in what the rate of asthma is in this population. So let's say our population is children in grades K through 12, and we want to know what percent of those children have visited an emergency room for an asthma attack. In the last 1 year, over the past year. So in New York City, I would guess there's 100,000, hundreds of thousands of kids in that age range in elementary schools in New York City. We certainly have enough schools. So let's say that, for instance, we don't have the resources to go and survey every kid in these schools. So we randomly sample 1,000 children. Okay, a little bit of a problem with this pad. Okay, it's randomly sample 1,000 children. And it turns out that, let's say, uh, let me make a number up here. Let's say that 110 of those children have visited the emergency room, and that leaves 890 who have not visited the emergency room. No, it's out of 1,000 people, 1,000 children that we randomly sampled. Okay, so what is the proportion of children in New York City that have visited an emergency room for an asthma attack? Well, if I look at this, it appears it's 110 out of 1,000, or in other words, it's 11%, 0.011. Okay, so that's what it looks like. The proportion of children, the percentage of children, the prevalence of asthma, or the incidence of asthma attacks requiring emergency room treatment in New York City might be predicted to be. Problem is that that's the proportion for our sample, right? That's our 1,000 kids that we sampled. The true population proportion is always going to be unknown to us, right? Unless we sampled we surveyed every kid in that age range in New York City. We're never going to know that unless we go and check everybody. But we have a sample of 1,000 kids that gives us a window into what that proportion might be. But we can't call it P, because if we call it P, we'll get it confused with the true population proportion. So instead, we're going to call that P cap, like that. Sometimes you'll see me refer to as P cap on a computer because it's a lot easier to write cap and put that little symbol, the little cap on top of that inverted arrow on top of the P, right? So this P cap is what that really represents. Well, because that's an estimate, just like X bar, that is a point estimate, an estimate of the proportion, an estimate of the middle of the mean value, and so on and so forth. These are called point estimates, right? So that point estimate happens to be 11%. But I'm not really interested in these 1,000 children. These 1,000 children are only a mechanism for me to estimate what the true value of the proportion is in New York, right? So I started really interested in. So just like when we had X bar, which I just scratched out, when I had X bar, in order to understand what the true proportion might be, I need to interpret that using a confidence interval. So let's say I want to find that 95% confidence for the true proportion of children in New York City that have visited a hospital for an asthma attack, an emergency room for an asthma attack. Well, again, it's going to be P cap plus or minus some value like a T score or a Z score or a Z score, either a T value based on sample or a Z score based on knowing what the variability is and the probability that we want, the confidence interval that we want, times the standard error. Well, when we do proportions, okay, we're almost always going to be using very large sample sizes, right? Just simple yes or no question, right? Have you visited emergency room? Not visited emergency room. So are you voting for Democrat, or are you voting for Republican? Are you voting to pass Proposition 1 or not pass Proposition 1, right? These are fairly simple surveys. So very frequently we're dealing with a large sample size. Okay, so we have two rules, okay? First rule is that in order to do what I'm going to do next, the sample size has to be at least has to be greater than 30. And there's a second rule here. Second rule is the yeses and the nos both have to be greater than 15. Right? You have to have more than 15 in each group. So in this case, we've got 110 yeses and 890 nos. I'm way over 30, which you're almost always going to be, right? And now, had the yeses been equal to 14, and the nos had been equal to 900 and 986, that was still a sample size of 1,000, but we wouldn't have qualified for our assumptions because one of the groups that we're examining is less than 15, right? So we want to make sure that we're working within the assumptions that we're starting with. Okay, so okay, let's go ahead and figure this out. So p cap I know is equal to 0.11. Okay, plus or minus, well, t or z score. Since we're dealing with a very large sample, we're virtually always going to be dealing with the z value for a 95% confidence interval. That's going to be 1.96. Okay, times our standard error. Well, what is our standard error going to be for a proportion? Our standard error is going to be equal to, whoops, it's going to be equal to, let's see, it's going to be equal to the square root of p times 1 minus p over the sample size. Okay, what's that going to be equal to in our case? It's going to be equal to 0.11 times 0.89 over the sample size, which is 1,000. Right? We're going to take the square root of that entire thing. So I'm going to get my calculator out here. Okay, so let's clear this. Let's clear this. And let's see. I'm going to take 0.11 times 0.89. That's going to be equal to 0.0979. And I'm going to divide that by 1,000. That's going to be equal to this nice small number that we round up with here. Then I'm going to take the square root of this whole thing. Everything I've calculated here, I'm going to take the square root of it. That's going to be equal to 0.00989. That's almost 0.1. I'm going to use 0.1 for our purposes. You should probably maybe keep a digit or two more in your case for the exam, and then round it, but only round really at the very end. Okay, so I'm going to take 0.00, I'm going to assume 0.001. So it's going to be 1.96 times 0.01. That's our standard error. Okay, so it's going to be 0.011, 0.11 plus or minus. So this is going to be 1.96 times this. That's going to be 0.0196. Right? It's going to be roughly 2%. Right? So again, keep a few extra digits here. Use your calculator or Excel. Keep a few extra digits here. I'm going to call this 0.02. So it's going to be 0.11 plus or minus 0.02. Right? So it's going to be, our confidence interval is going to be 0.09 to 0.13. What does this tell us? This tells us that we're 95% confident, based on the sample size, based on these results, that the true population proportion is between 9% and 13%. When you do it, it might be 0.91 to 1.31 or something like that. But so keep an extra decimal place or two until the very end. You can round at the very end, most likely. Okay, so maybe an extra digit here would be good. So at any rate, so this is our 95% confidence interval. What does that confidence interval mean? That means that we're 95% confident that the true population proportion lies between these two values. Okay, so which gives us a better window into what we really know about the true proportion than just saying that sample size of 1,000, we got a result of 11%. This gives us a better window on what we know about it. Okay, so someone just put their email up, and I'm not sure why they did. Do I need to send you something? But I'll get back to that. Okay, so keep in mind now that what kind of variations might you wind up with here? One of the variations that you might wind up with here, and also when we're calculating the confidence interval of the mean of a numerical variable, is that you might be asked for a 90% confidence interval or a 99% confidence interval. instead of a 95% confidence interval. Well, the only difference there, oh, no problem. That's okay. I got a response there. The only problem is that the only difference is that in the case of a 99% confidence interval, our confidence interval has to be wider to have a higher level of confidence that we've captured the true population mean or proportion. So instead of using 1.96, we would use 2.58. 2.58. And so since it's a bigger number, we're multiplying our standard error by, then that's going to give us a wider range, so we're more confident that we're going to capture the true population proportion. And if we're satisfied with a 90% confidence interval, we could use 1.64. If you guys go back over all the old material, you'll remember that we got that 1.64 and that 2.58 from the normal distribution. This is 90% of the results are between this number standard deviations or standard errors below the mean and above the mean and so on, right? And this is 99%. If we're using the t-table, you would you'd be able to do the same thing by going over here to 99%. So for our example here, was 35 degrees of freedom. Here's our 30. Oh, I don't have 35 here. 35 degrees of freedom. Did I do 35 before? Did I pick the wrong one out? Oh, I must have gone 25, right? I might have made an error there, right? So at 35 degrees of freedom would be roughly between these two numbers. It would have been 2.03 roughly, right? You could either take the more conservative number, which is 2.04, go down, or you can interpolate between the two of them. Since it's right in the middle, 35, we could say the average of these two and use 2.03 instead of 2.04, for instance, right? So it would be that. But if we wanted a 99% confidence interval, we would use this column instead. And this column would give us a value of something like around 2.72, right, in between these two. Yeah, I use 25 degrees of freedom. When I'm rushing, trying to look at the chat box, trying to look at this, trying to remember these numbers, I keep making mistakes like that. Comes with age. When you guys are older, you'll understand. So at any rate, I'm glad. You should tell me about these ones. Let me know when I make an error like that. Okay, good. So at any rate, but you guys get the idea here. You would use this column if you're looking for 99% confidence interval for the t-score, and you would use this column if you were looking for a 90% confidence interval. Right? And you can see no matter what confidence interval, no matter what the t-score, no matter what your sample size is, the t-value you're going to use for 90% is smaller than the one for 95, which is smaller than the one for 99. Okay, it's still always going to work the same way. Okay, so that's as I think adventures we'll probably get as far as the confidence intervals for proportions. There's going to be other stuff that'll come up. So let's take a look at this idea of t-test, hypothesis testing. Okay, now hypothesis testing, what we're doing there is we are taking the information that we know about from a sample about a population, and we're making a prediction about whether or not what level of certainty that we have that we can say that two populations are different from one another. It means the two populations are different from one another, that the mean of a population based on what we know, based on a sample, is that population mean is really different than than a known mean for another population. That's a single sample test, or that there's a difference between before and after levels or scores for individuals. That's a paired sample test. Okay, so we're going to start with a single sample test since that came up, and that's the easiest one to work with. So let me see if I can't come up quickly with a data file that'll do that for us. I'm going to work with the one that we actually had in class because they're really pretty much going to always look the same. So here's our data for a single sample test. Okay, and in fact, it's all worked out here. I'm going to get rid of all this stuff so that we can start from scratch. Okay, here we go. So here's our scores, right? This is the variable is x, whatever that is. It might be a test score, let's say a motor score, a psychological test, whatever it might be. So this is a sample of 9 people, right? Sample size is 9. 9 people that took a let's say a psychological test, took a psychological test, and this is the scores for each of those 9 people. Now, we're really not interested in what the mean x bar, we're really not interested in what the mean is for this sample. I'm going to calculate it anyway right now. Oops. Okay, so I'm going to calculate this average, this mean. Turns out the mean is 9.89. And I'm really not interested in what X bar is, right? I don't really care about X bar. I really care about mu. I want to know what the population mean is, right? So in order to know what the population mean, I would have to sample the entire population. I only have the resources to randomly sample 9 people out of that population. So the best I can do is X bar, the mean of that sample. So now, let's say that I have another population here, call it Y, population Y. Okay, and I happen to know that mu for population Y is equal to, I'm going to say 9.0, right? So I'm interested in knowing whether the psychological test scores for population 1, population X, is different from the than the mean for population Y. Okay, how would I state that as a hypothesis test? Well, I'm only interested when I state my hypothesis test. I'm only interested in the means of the population, not of the sample. So I would not say X bar 1 is equal to X bar 2. Right? I wouldn't say that because I'm not interested in comparing X bar 1 and X bar 2. I'm interested in comparing the mean for population X, whether or not that's equal to, whoops, the mean for population Y, right? So that's really what I'm interested in. Are they equal to one another? Or are they not equal to one another? Let's see if I can't get that to type in there automatically and just change this. Oops, I'll do it up here. Not equal to each other. Okay, that's really what I'm interested in demonstrating. Okay, so now I know the mean. I already know the mean for population Y, don't I? Don't I? It's equal to 9. So really, I could, instead of saying this, a better way for me to say it would be the mean for population X is equal to 9, or the mean for population X is not equal to 9. Right? Isn't that a better, more compact way of saying the same thing? Because I happen to know what the other population is. That's what makes this a single sample t-test. I'm comparing a mean that I know to a mean that I only know from a sample, right? So our sample result, X bar is 9.88, but that's as close as I know to what actually the mean is from the population that was drawn from. But I happen to know the true mean of this other population. Happen a lot, not so much. These are come in more commonly into use when you're comparing a sample of performance against a standard. Let's say you wanted to know, you predicted ahead of time that the average passing score on this should be 10, right? And you're comparing it to what the actual was for a group of people, a population that took this test without testing everybody in the population. So you might be saying, well, is the average for this if I gave this test to its entire population, would they score above 10 differently than a score of 10? They score better than 10, less than 10. Would it be different than 10? Can I predict it would be different than 10, better or worse? Right? So either way. So in order to do that, we're going to have to see if these are different enough. If X bar is different enough, which is our substitute right now for what mu is for the population we're drawing from, is that different enough from 9 for me to say with 95% certainty that that this is true, that mu of population X is different than population Y, in other words. Or if I can't prove that, then I have to just, fail to reject the idea that they're not different. Okay, not say that they're the same, right? We're not proving that. We're just failing to say that they're different when we do this. Okay, so how do we do this? Well, first of all, we know what the population, the mean is for the sample, which we're going to use as a surrogate for our mean for the population. Well, now, I need to know how many standard errors apart that these two values are going to be in terms of the variability that we see for the population from the sample that we took, this sample. I need to know what the standard deviation is for our sample. Okay, the standard deviation for our sample is going to be equal to 2.93. So now the standard error, that's the variability of the sample, the people in the sample itself. What's the variability of repeated samples of size 9? Well, that's our standard error, and that's really what we're interested in. So click in here, equals, it's going to be equal to, and what was it again? It's equal to the standard deviation divided by the square root of the sample size. In this case, sample size is 9, so I'm just going to put in a 3 here. So our standard error is equal to 0.9781. So if we're going to do a confidence interval for X bar, we would say X bar plus or minus the t-score for 8 degrees of freedom, right? Whatever that happens to be, right? The t-score for 8 degrees of freedom times the standard error. And then we take that calculated margin of error, we add and subtract it from 9.88 to see the range that we're 95% certain that the true population mean would be for the population that this sample was drawn from. Instead, when we're doing hypothesis testing or single sample t-test, we're instead going to calculate how many standard errors apart these two values are, right? So what is that going to be? What's our formula going to look like for that? Our formula for that is going to be t is equal, in other words, the number of standard errors apart is going to be, and how we calculate number of standard errors apart? Well, we're going to take X bar minus mu, the mean for that known population. I'm going to put parentheses around here just to keep things clear. Divided by our standard error. Oops. Okay, so let's see what that means. That means that let's say that X bar were 100 and mu were 90 and the standard error was 5. So 100 minus 90 is 10. Standard error is 5. 10 divided by 5 would be 2. The difference between these two are 2 standard errors apart. It's 2 standard errors difference. In our case, what is it going to be in our case? It's going to be equal to X bar, which is 9.88, minus 9, right? I'm going to put that in parentheses, so it does that addition, that subtraction first, divided by our standard error. And that's how many standard errors apart that our sample is. Okay, and it's 0.9. It's about 1 standard error apart. Well, we know when we're talking about 95% confidence, we're talking about standard errors in the range of around 2, right? So that's our value. That's our calculated value for P calculated. So now I need to know, are they far enough apart for me to say with 95% certainty that the mean for this population is different than the mean for this population? Well, in order to predict that, I would have to look up what my critical value of P is. How far apart do they have to be in order for me to say that it's different enough? Well, if we're a really big sample, really big sample, over 100, right? We could use the normal distribution Z, and I could say T critical is 1.96 for a really big sample, or in a case where we know what sigma is for population X, right? For really big, we could just use 1.96. But the sample size is only 9. So our critical value of T is going to be bigger than 1.96. In other words, we have to be more demanding. T calculated has to be bigger. X bar and mu have to be further apart for us to be that certain. So let's go over to our T table again. Hopefully I didn't put it away. If I did, I can always bring it back here. Let's see. Bring it back up here. Okay, so for 9, sample size of 9 and 8 degrees of freedom, what does our T value have to be? 95% confidence, right? It's going to have to be 2.62. Okay, so our critical value of T is 2.62. Okay, so we're only going to reject our null hypothesis if our calculated value of T says that X bar and mu are far enough apart that we are 95% certain that we're not going to be incorrectly. I did it again. Thanks for pointing it out. 2.306. Good. I'm glad you're doing that. Did I get it right this time? 8 degrees of freedom, 2.306. Yeah, you even got it in the wrong column. 2.306. Good, thanks. Okay, so do we have enough confidence to say that they're far enough apart? Well, in order to say with 95% certainty that they're far enough apart, in other words, only be wrong 5% of the time or less, they would have to be this far apart, 2.3 standard errors apart. In fact, they're less than 1 standard error apart. So in this case, we fail to reject the null hypothesis. Okay? So instead of using the idea of 95% certainty, right? Instead of this idea of being 95% certainty, we instead, when we do hypothesis testing, we instead choose an acceptable level of alpha error, type 1 error or alpha error. In other words, probability that I would be wrong when I reject the null hypothesis, right? And mostly, most of the time, we're doing the same thing as 95%. We're saying that we're willing to accept an alpha error of 5%. Right, or 0.05. Okay, so really kind of saying the same thing, isn't it? Right, so in this case, we failed to reject the null hypothesis. Well, let's say that that mu was equal to, instead of being equal to 9, was equal to 13. Whoops, 13. How would that have changed things? Okay, let's take a look at that. Okay, instead, we would have had 9.88. Whoops, I'll bring that back. Instead, we would have had 9.88 minus 13. Oops, I'm going to put in the 13, right? Parentheses. And I'm going to divide by the standard error. The standard error is here. See how many standard errors apart this is. This is 3.18 standard errors apart. Okay, is now that these are far enough apart. Our sample 9.88, our prediction of about what approximately what the population mean is for this population, for population X, right, is far enough apart from what we know the population mean could be for population Y, right, that's a known value, far enough apart that we can, with less than 5% chance of creating a type 1 error, an alpha error, that with less than 5% of that happening, we can reject the null hypothesis and accept the alternative hypothesis. Okay, so that's really what we're looking for here. That's what we're after here. Okay, so the sample size is important in both confidence interval and in when we calculate our t-value to decide whether we can reject our null hypothesis. It plays the same role, really. makes up for the fact that you don't know the true standard deviation of the population that you're working with. Now, I believe I have this same sample as a SPSS file. And I'm going to open that up. Okay, in a moment, I guess it will open up. Matter of fact, maybe it's down here already. That's not it. Oh, here it comes. Okay, a little slow starting up. Oh, here it comes. Okay, here we go. Oh, actually, I have a couple of examples there. Have that one too. Let's see what windows we have here. What we actually have open here. Oh, each wall. Up, still opening. That's what the issue is here. Yep, there we go. That's our file. Okay, so there's our file. There's our values here. Okay, so I can go to Analyze. I want to run my t-test. I'm going to compare it to a value. I'm going to use, this time I'm going to use a value of, let's say, 12. Analyze. I'm going to go to Compare Means. I'm going to go to one sample t-test. We know the mean of one population, but we only know the other population from a sample. So if one of those is known as a sample, the other one is a known mean. So that's a single sample t-test. I'm going to put a single sample t-test. Since only one of them is a sample, I move that variable to my test variable. And down here for test, to my test variable, for test value, I put in the mean for the other population, for the population that's known. So I said I was going to use 12 this time around. Right, so I'm going to click OK. And SPSS will bring up the output window with the results of our t-test. It'll do exactly the same math that we did before. And it tells us that our t-value is 2.158. We're interested in the magnitude here, the number of standard errors apart. We're not too concerned. We're not concerned about the negative or the positive sign. That's going to change depending on whether your sample or your mean happens to be bigger or smaller than the other one. We're really interested in the difference here, right? How far apart they are. So as it happens, it's 2.158. Looks pretty good. But you know, it's a small sample size. And I think we said we needed something like 2.3 for the critical value of t. So it doesn't look to me like we've exceeded the critical value of t when we compared our sample result, which was 9.89, to our known mean of 12. Doesn't look like that is quite big enough. And in fact, if we go across here, the significance, two-tailed significance, that's the p-value. The p-value is the probability you would be wrong if you reject the null hypothesis. That's the probability that if these sample means were the same for population X and population Y, that you would get this extreme a difference between these two when you took a sample size of 9. What's the probability that you would get that big a difference? It's going to, even if the null hypothesis is true, that's going to happen 6% of the time. So you would be wrong 6% of the time if you said I could reject my null hypothesis at this point. You need that p-value, what SPSS called the significance. You need that p-value to be less than 5%, or alpha. In other words, p that you calculate has to be less than 5%. It has to be less than alpha. In other words, in this case, less than 5%. It's not less than 5%, so we fail to reject the null hypothesis. Had I put a 13 in there, we know that we would have succeeded, right? Let me do it again. Analyze, compare means, and sample t-test. I'm going to change that to 13, and we know we're going to succeed because we did it in Excel. And there we are. And look, there's a p-value that we calculated before. And our p-value, our significance, is less than alpha, less than 0.05. So we reject the null hypothesis. Okay, how do you guys feel about that? Are you okay with that? Hope I haven't put you guys completely to sleep here. Okay, good. You know, it's a little bit of a lag as I wait for your responses here. Okay, good. All right, good. So let's move on from there to a two-sample t-test. And a two-sample t-test, okay, we actually have, we don't know either population mean, right? The only thing we know is the results of our sample. So here is an example of histidine. I don't know what, yeah, I'm not sure what this stands for. I don't have any other information on it. I have two things here: a numeric variable, a scalar variable. This is a nominal variable. It's only ones and twos, right? A scalar variable, right? Male and female. One is male, two is female. Okay, and a numeric variable called histidine. And I suspect that might be some sort of hormone or something like that. So we're comparing whether or not males and females in this population have a difference in the amount of, I'm guessing, this hormone. Okay, doesn't matter what it is really. We're really more interested in the numbers right now, right? So we want to compare these two, right? So looking at this, I say to myself, okay, so I have a sample of 5 males and 5 females. I can go up here to view and value labels to see which is which, right? Male and female. Okay, but you know, I'll leave it. Remember, that's really 1 and 2 is the way it's inputted. It only knows that it's male and female because when we coded SPSS, we told it 1 represents men, 2 represents women. Let me go back here. Okay, so I want to compare the mean for this sample, X bar 1 to X bar 2, X bar for men to X bar for women. I'm not really interested in the difference in the mean of this sample versus the mean in this sample. I'm really interested in all, oh, thank you, amino acid, thank you. Oh, yeah, it is. Of course it is. Right, of course it is. Thank you. Okay, so I'm not really interested in the mean for this sample versus the mean for this sample. I'm really interested in for all women from this population, for all men from this population, if there's a difference, right? So let me go over here, open up a blank sheet of paper, and I want to compare these two. So first thing I'm going to do is I'm going to establish my uh, my uh, 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 my hypothesis, my null and alternative hypothesis. So my null hypothesis is the mu histidine for men is equal to the average, population average histidine for females. My alternative hypothesis is that the two means are not equal to one another, right? I only know the population means themselves. I don't know the sample. I only know the sample means. I'll never know the population means. So I'm stuck here using the sample means to try and make a prediction about it. So the next thing I need to establish, what level of certainty am I willing to deal with here? So I'm going to say alpha has to be equal to 0.05 for me to reject the null hypothesis. I want less than 5% chance that I would get as extreme a difference in the values of the two sample means if the null hypothesis is true. So I want my p-value, my significance, to be less than 0.05. So I'm going to go back to SPSS, and I'm going to say analyze. I'm going to say analyze, compare means. In this case, we have two samples, two independent samples, a sample of men and a sample of women. So that's an independent sample t-test. And in this case, let's move this back over here. This is the way it would open up normally. Okay, in this case, our test variable is a numerical variable that we're finding the averages of. So we're finding the average of this, the average level of this amino acid. And my grouping variable is going to be the two groups that I'm comparing. In this case, the name of the variable is called group, but it actually represents male and female. Now notice, SPSS is not happy with this yet. It wants to know what values define this group. It's not men and women. Remember, in the background, it's really 1 and 2. Okay, 1 and 2 are already filled in here. Most cases, you would have to fill it in yourself, right? 1 and 2. So now SPSS understands, oh, we're going to compare the mean for the group 1's men to the mean group 2 females. In fact, I think it's actually, is it the same sample size? 6 women and 5 men, even a different sample size. Okay, so I'm going to go ahead and I'm going to click OK. Okay, okay. So SPSS is going to bring up the output table, the output window with our result. And let's see what it tells us about this. Well, first of all, the mean for men is 219. The mean for women is 163. Now it's our job to find out whether or not that difference is more than 2 standard errors apart, or whatever the t-value is based that we need it to be based on the sample sizes that we're working with. Okay, so one of the decisions we have to make at this point is whether or not we can assume that the standard deviations of these two groups is equal to one another. In other words, we're looking to prove that the means are different, but we didn't say anything about the variability has to be different, right? So even though the mean for women is lower than the mean for men in our samples, right? Well, maybe the variability, like the range for women is 30 below this, 30 above this, and the range for men is 30 below this, 30 above this, right? Very frequently, even though the means will be different, the variability within each group will be the same, right? So let's take a look at what it is. Well, one is 32, one is 41. Now, keep in mind, this is not an entire population. This is only a small sample that we looked at here, right? So the idea here now is that if we could, all we know about the mean for men is what we know from the 5 people that we sampled. All we know about the mean for women is from the 6 women that we've sampled, right? So these means are based on a relatively small sample size, right? So, and in fact, then that implies all we know about the variability for men is based on 5 people and variability for women based on 5 people. However, if we can assume that the standard of variability, standard deviation for these two groups is the same, well, then we can group these together, get a weighted average, and say, well, we can base the standard deviation on a sample size of 11 instead of 5 or 6. Right? So it gives us more power in predicting whether or not, in the ability to do our analysis, right? So that's a good thing for us if we can compare them. When we work with Excel in solving this problem, we don't have an easy mechanism for analyzing whether or not we should pool these samples or not. So we use kind of a rough rule. Okay, we say that as long as one is not double what the other one is, they're close enough that we're willing to take the risk of pooling the samples by combining the standard deviations into a single value for predictive purposes. Okay, so in this case, we would have said, yeah, we can pool these samples. Why not, right? SPSS does this a little bit more rigorously than we would do it in Excel. If you look down here to this table, oops, got a little bit of problem. Yep, I'm reconnected. Okay, if you look down here for this table, right, you can see that SPSS has an area here from here. I'm going to move my cursor up and down. From here to the right represents our t-test. And in fact, it does a t-test twice. It does a t-test, this top row is a t-test, this bottom row is a t-test. It does it twice. The first time it does it, pooling the standard deviations, assuming that the variance is equal, and pooling the standard deviations. It does it again, assuming that standard deviations are not equal and not pooling them, right? So if I look across here, based on what my conclusions were here, I would use the top row here, right? And the top row would tell me my t-value was 2.42. Now, for when we pool these standard deviations, we get our degrees of freedom from the sample size of group 1 plus the sample size of group 2 minus 2. Okay, so that's there were 5 men, so that would be 4. Excuse me, 5 men, and there were 6 women, so that would be 11. Minus 2 would be 9 degrees of freedom. 9 degrees of freedom was about 2.3 or 2.2 or 2.3 or something like that for our t-score. Right, so it looks like our t-value is bigger than we need to reject the null hypothesis. And in fact, if I look at my significance, my p-value is 0.038. It's less than my acceptable level of error. which is 5%. So my level of error is less than what I would have needed to reject the null hypothesis. So in other words, we can reject the null hypothesis because it's less likely I would be wrong than what I'm willing to than my maximum amount of error I would be willing to accept. Maximum amount of error I would be willing to accept is my alpha, which is 5%. This is smaller than alpha, so I have confidence that I can reject my null hypothesis within those parameters, right? So this line tells me I can reject my null hypothesis, and that's what my t-value is. Had I assumed equal variance is not assumed, the calculation would have been different. And instead of getting this t-score, I would have gotten this t-score, and I would have gotten this significance. It's kind of odd sometimes when you use SPSS, you get some odd results here occasionally. But in this case, I would have used the top line rather than the bottom line. Now, SPSS does do a test for the equality of variances. Okay, so let's take a look at this test that it does. These first two columns here are Levine's test for equality of variances. It works just like you would work your other hypothesis tests. It assumes equality, and you have to prove inequality, right? Reject the idea that there's an equality in order to accept the idea that there isn't an equality, right? So, in other words, our assumption is that the variances are equal. In other words, our assumption is use the top row, unless the Levine's test gives us a significance less than 5%. Significance 0.38. That means we can't reject the idea that they're equal variances and use the bottom row. We have to stick with the top row. In other words, we've got the same result here as we got with our assumptions that we used up there. Okay, so in other words, if the significance for Levine's test is not less than 0.05, you don't reject the idea that the variances are equal, and you use the t-test that exists on the top row. Okay, so now that's how we would deal with that. Now keep in mind that if you had to do this calculation manually, right, for this t-test, let me see if I can't find it quickly. Samples. Let's see, t-test variations. I think it's this one. There we go. If we had to do this manually, what would this look like? We had to do it manually for a single sample t-test. You would go through this, which is exactly what we did when we did it with Excel. But if we did it for independent samples, well, we would need to calculate a pooled standard deviation if we assumed the standard deviations to be equal. So our t-value would be to be equal to x bar minus x bar for the first group minus x bar for the second group. No big surprise there. Divided by our standard error. Now our standard error becomes a more complicated calculation. It's our pooled standard deviation times the square root of 1 over the sample size of group 1 plus 1 over the square root of the sample size of group 2. Whoa, that's a bit complicated. Boy, it'd be nice. It's nice that if we can use SPSS for these calculations instead of Excel or instead of a calculator, because you got to do complicated. Well, even before you can resolve this, you know x bar 1, easy enough to calculate in Excel. X bar 2, you know, so you can calculate the difference. The square root of 1 over n1 plus 1 over n2, well, you know the sample sizes, so you should be able to get that. But it needs the pooled standard deviation. So before you can even do this, you have to calculate the pooled standard deviation. And that is the square root of sample size 1, which you know, minus 1, times the standard deviation of group 1, which you can calculate using Excel, right, squared. You take that and square it, right, plus the sample size of 2 minus 1. In other words, in this case, it would have been 6 minus 1 or 5. This would have been 5 minus 1 or 4 times the standard deviation of that second group, the women, for instance, in this case, squared over n1 plus n2, which is 11 minus 2. That's over R9, right? Same as R9. So you would have to resolve this formula, calculate the pooled standard deviation, and then use it in this lower formula to calculate t. And then, knowing it's 9 degrees of freedom, right? Degrees of freedom is n1 minus n2 plus n1 plus n2 minus 2. Knowing it's 9 degrees of freedom, look up the critical value of t to determine whether your calculated value was larger than your critical value, so you can reject your null hypothesis. Well, things get even sloppier here when you have to, when equal variances are not assumed. In some ways, they get a bit sloppier, right? In fact, the calculation is actually a little easier. If equal variances are not assumed, for instance, if the standard deviation of one group had been had been 32, and the other, instead of, I think, around 45 or something like that, or 42, instead of that it had been 75, one would have been more than double the other. So you would not assume the standard deviations of the variability to be equal. So you would use this formula to calculate t instead. You don't have to calculate full standard deviation here, but you do calculate x1, x bar 1 minus x bar 2, same as we did before, over the standard error. In this case, it's going to be equal to the square root of the standard deviation of group 1 squared over the sample size of group 1, plus the standard deviation of group 2 over the sample size of group 2. Add them together, find the square root, and divide that into the difference between the two means to calculate your t value. Well, in order to get your t critical, you need to know the degrees of freedom, right? And to calculate the degrees of freedom here, it's not just n1 plus n2 minus 2. In this case, it's this ridiculously complicated formula. In most cases, what you'll do is you just take the smaller sample size, like 5, subtract 1, 4, and use that for your critical value of t. That's a very conservative way of approaching this. Okay, so, and in fact, you'll miss, if you do it manually, you're going to miss some cases where you might have been able to reject the null hypothesis. But you'll notice that it's very complicated. So very frequently, if you're doing it manually, just do that. Just take a smaller sample size, subtract 1, use that degrees of freedom to look up what the critical value of t would be. In fact, if I go back to SPSS, assuming I haven't closed that yet, you'll notice that if we had used the bottom line here, look at what the degrees of freedom would be. It's a really freaky number. It's not a whole number like it is up here because it's based on that formula. In both cases, you wind up rejecting the null hypothesis, however. Okay, so that's how we would deal with that. Now, paired samples is another story. Paired samples are a situation where we might be having someone take a test, a physical, a measurement or something like that, where we're taking measurements from the same subject, say before and after some intervention. So what would that look like? So for a, let's see, oh, wrong file, wrong folder. Okay, I'm gonna end with this. I'm gonna have another session within the next couple of days where we're gonna cover the chi-square odds ratio and relative risk. Okay, so let's see. So you'll have that, a preview of that before you take your first shot at the exam. But I want to get to this last part. Okay. Chi-square, maybe it's here. This sample. Here, I think it's in here. Let's see the sample. Here we go. Paired samples. Actually, I was hoping to have a. Okay, I'm going to open this up in SPSS first, and I'm going to move the data into. There we are. There we are. Okay, so I'm looking for the new data file that I just opened. Nope, still hasn't opened up. Try it again. Looks like it wants to open up. It'd be easier if I just do it this way. Open, data, and navigate to, here we go. Here we go. Okay. That's probably going to open up 9 times again now. They tried it so many different ways. Okay, so here we go. So here is some measurement, right? Could be a test score, could be a physical measurement, could be a chemical measurement, but it's some test score. But subject one is measured before and after some intervention. Subject 5 is measured. Yeah, I knew this was going to happen. Okay, we don't need that now. Subject 5 is measured before and after this intervention. So the idea here is we want to know whether or not the intervention that went on between these two made a difference. Whether they got a higher score or a lesser score. I'll leave this one open. Have a lesser score or a higher score based on the difference. Well, we could have done this study two-way. Oh man, it's, I hopefully won't open again. We could have done this study two ways. I could have gotten group one and left them naive, not done the intervention, not given them the drug, not giving them the training, had them take a test, right, and got a result for group one, and then compare them to group two, another group that's similar to them, same age, same weight, same BMI, same smoking habits, whatever, right? Group two, have them give them training, give them an intervention, give them a drug, and see if there was a difference between the values that I got for the people that were taking the drug versus people who were not taking the drug. Well, the problem with that is that there could be a lot of reasons why there are differences between these people that didn't take the drug, got a placebo, and these people who did take the drug or did do the training. There'd be a lot of reasons other than the training itself, right? So who knows what variabilities could be in there, married, unmarried, insured, uninsured, that might have had some confounding effect on our comparison, right? So to eliminate all of those, well, subject number one, his BMI was the same before and after. His smoking status the same before and after. His age same before, roughly the same before and after, right? So instead of worrying about whether or not I have to have all these other confounding factors, why don't I just look at this person's level before, his level after, and just compare the differences, right? So I'm going to take this and I'm going to put it into Excel. I'll get a new workbook and I'll blow it up so we can see it. Okay. I'm going to paste this in here. Okay, what were the variables called there? After and before. Okay, I'm going to insert a row. Okay, so this is after, and this is before. This is the work before. So now what I can do is I can say, well, I'm not so worried about what are those actual values, right? I'm actually worried about what the differences were. Did this have a difference? Did it have an impact? Equals after minus before. So for this person, their score increased by 31. Well, I can do that calculation for every one of these people in our sample. And here we go. There's all our differences. Well, now, instead of worrying about these numbers, I can forget about those numbers. I can instead just look to see what's the average difference. Right? What's the average difference equal to? It's equal to average. And I'm just only going to look at these values right here. Okay, the average difference is 12. Well, if there was no difference in the performance of this placebo, my battery must be getting low. And my mouse, hopefully will reconnect again. There we go. I don't see my cursor. I think it's trying to connect. I'm going to have to use my little cursor here for the moment. If there's no difference between these two, right? If the drug or the intervention has no effect, Why not before minus? It doesn't matter. Jorge, it doesn't matter because what we're looking for is a difference between these two. In other words, is there an effect? Does it go higher or lower? We're not really interested right now in whether it's higher or lower, because you'll see that now when I define my null hypothesis. What's my null hypothesis going to be? Right? My null hypothesis is going to be that the difference between these two, right, is the difference between these two. In other words, mu1 minus mu2, right, is equal to 0. In other words, there's no difference. Nothing changed. So our alternative hypothesis is going to be, on my mouse came back, is mu1 minus mu2 is not equal to 0. Okay, or I could have just said the difference is equal to 0, difference is not equal to 0. That's our null and alternative hypothesis. Okay, so now at this stage, I want to prove whether or not the average, if I applied this to an entire population where these 16 people were drawn from, if I applied this test or this intervention or this drug to this entire population, would there be a difference between the values for the average for the entire population before and after? In other words, is this true that there would really be a difference for the entire population? Remember, mu means the entire population, right? Well, the difference I got here was the difference between these two samples. In other words, it's an X bar basically. So what am I doing here? I'm comparing this difference to the value 0, right? So I'm comparing this difference to the value 0. So in a sense, what I'm doing is I'm comparing the mean of this group to a certain value. Well, isn't that the same thing as doing a single sample t-test? Except the difference now is our sample. Our sample is the difference, and we're comparing it to the value of 0, right? So I can calculate my standard deviation for the differences. That's going to be equal to this. And I'm going to cancel my calculate my standard error. And that's going to be equal to my standard deviation divided by the square root of the sample size. Sample size is 16, right? So that's going to be equal to 4. And then I can calculate my t-value. And my t-value is going to be equal to the difference, difference for the group, for this group, minus the value I'm comparing it to, which is 0, divided by, okay, and I'm going to put parentheses around here, my standard error. And my standard error is equal to 3.04, 3.403. So my t calculated is equal to 3.58. My t critical, and how do we get t critical for a one single sample t-test? It's the sample size minus 1. Our t critical for 15 degrees of freedom. Okay, I'm not going to look it up right now. I'm just going to estimate it. I'm going to say it's roughly equal to 2.1, let's say, right? So my t calculated is bigger than I need it to be to reject the null hypothesis. So I can go ahead and reject the null hypothesis and reject the null hypothesis that mu1 minus mu2 is equal to 0. In other words, there's no difference, and accept the alternative hypothesis that there is a difference. And if it had been less than 2.1, I would have failed to reject the null hypothesis. Right? Doesn't mean the difference is 0. This means I failed to prove that it wasn't 0. Okay, so if I do that with SPSS, and that's the last thing I'm going to do right here. If I do that with SPSS, I'm going to go to Analyze. I'm going to go to Compare Means. I'm going to go down to Paired Sample t-test. And I'm going to move, notice it needs 2 variables. It needs the result for group before and for, it's not always going to be before and after. There may be some other way of measuring differences here. and after, right? And I'm going to ask it to go ahead and calculate my t-score for that. And an output window should come up here, and here's our output window. Notice that there's no two rows here. It's only a single row because we're only comparing the single sample to the value 0, and our t-score comes up just the way that we found it before, which is equal to 3.58. Notice our mean, our standard deviation, our standard error, same thing we calculated in Excel, and our t-value is 3.8588. We know t-critical was going to be roughly 2.1 or something like that, and it was 15 degrees of freedom, it was going to be 2.1. So we know that our t-value is bigger than t-critical, so we're going to reject our null hypothesis. But SPSS confirms that for us, telling us that the probability we'd be wrong if we rejected the null hypothesis is indeed less than 5%. In fact, it's less than 3%. So that's actually 0.3%. So we can reject the null hypothesis and accept the alternative hypothesis. Okay, so I'm going to post this, and I will do another maybe brief session that's going to cover chi-square and odds ratio and relative risk. We kind of covered a little bit of that in the review session as well. So yeah, if you look at the review session, it should be on the announcements from Thursday. I got for those of you that tried to log in, I got started a little late because I got caught in that mess, driving in that mess on Thursday. So we started, I think, about 20, 30 minutes late, but we went a little bit longer instead. So thank you for the few people, a couple of people that showed up in class there to be there with me. Right, so that's posted on Blackboard, so you can watch that review session. It was primarily on odds ratio and relative risk and confidence interval. But I will cover that a little bit more here, especially if people post questions on and that little thing on the forums there for review session questions. Okay, so again, I'll have the exam will be posted on Wednesday, so you can get started on it. And I'll probably make it due like Tuesday, like end of day on Tuesday, not Monday. So if you're going away for the weekend, you have that extra day on Monday to work on it in case you can't get to it over the holiday. And if I don't talk to you again, if you don't wind up tuning into the next online session, have a great holiday, and I'll be back in touch with you in the next few days.